Oh, welcome everybody. It's now 6:01, April the 16th, 2020. It's time for our lecture. Today is our last lab, and it's a fairly short lab on electrochemistry. We didn't have, or unfortunately, we couldn't do the two labs I had scheduled for us at the beginning of the semester. So tonight will be our last virtual meeting. It has been a pleasure being your instructor this semester. Uh, what I want to do is just cover what you go over the theory a little bit to walk you through what's all about in terms of electrochemistry, in terms of electrochemistry, so that when you get to calculation, you'll be in a position to fill in the data sheet, a tighter calculation before you submit. Uh, I hope you have your lab manual before you. I'll be referring to some pages, some equations. You should also have a pen and a paper, and I'll walk you through the calculation. You partially have, or you have a data sheet, which is um, partially filled. There are some section you have to do the calculation to fill in with. I will share my screen here and show you the background, all right, the background of the procedure. I will share my screen and walk you through the procedure. All right, let's see. I'm going to show you the, can you see my screen? Can you see my screen, please? Can you see my screen? Electrochemistry?
Yes.
Yes, thank you. What is all about electrochemistry? I know when the term electro comes from the word electricity, or you know what electricity is all about. Every now and then you drive down the street, you see the cables. It's about the electrons being transferred from point A to point B. When you charge your phone on any electronic device, it has to do with electrons being transferred. In the previous experiment, and I believe in your lecture, you have covered uh, this chapter on electrochemistry. You know what oxidation is. This was Chem 1 concept, reduction, oxidation, reaction. Maybe back then in Chem 1, you only had to define what is oxidation, what is reduction, all right? And those are the terms you should know for this lab. You should understand what is all about redox and reduction oxidation. There are 6 terms which goes into this chapter on electrochemistry, which is a challenge across the nation for all Chem 2 students. And these are: one, you should know the difference between oxidation reaction and reduction reaction. Those are 2 terms. Reducing agent and oxidizing agents make 4 terms. What is being reduced and what is being oxidized? You should know those terms, all right? Uh, Electrochemistry is basically the study of generation of electricity. And there are two types of cells used to, all right, used to generate electricity. A cell is basically a device used to generate electricity for electrons to move from point A to point B. Now, before I get to those 2 types of cells, you should be able to define oxidation. It is the loss of electrons, reduction, gain of electrons. What is being reduced? What is being oxidized? Remember, traveling agent does not travel. It's make people to travel. So oxidizing agent make the other stuff to lose. Reducing agent adds electron to something else. If you look at this equation right here on the screen, if you look at the on my screen, there is an equation here which I want you to look at. This is reduction. We are adding electrons. This is oxidation. We are losing electron to become positive. Remember, electrons are negatively what they are negatively charged. So if we are losing two from a neutral atom, all right, we end up with a positive two depending on how many electrons are lost. So the overall charge tells you how many electrons are transferred, not really lost to, into some space, but it is acquired by other atoms in the reaction. So oxidation, reduction take place at the same time, and you should be able to see the reduction oxidation. This is reduction. You are reducing ion here, and please get into configure your brain to know that, or your mind, what is being oxidized, what is being reduced. How do you know? It is by keeping track of oxidation state or oxidation number. I don't want to get in details into the oxidation reduction stuff. You can read that. I know you covered this in Chem 1, in Chem 1. However, this is the foundation of our lab today, in the sense that unless we know how many, or we are not in a position to figure out how many electrons are lost, and then the calculation part would be a challenge. So right now, from this slide or from this page, oxidation, or how do you know that a species has lost electron? Is by keeping track of the overall charge. The overall charge tells you how many electrons are lost, how many electrons are lost. So having said that, there are two parts in our experiment today. There are two parts. There is part one, part two, all right, or A and B, A and B. Now, there is what we call standard electrode potential, and or basic electromotive force is the ease at which a species is reduced. And remember the superscript from the last discussion, from our last experiment. Superscript node stand for standard state. This superscript node stand for standard state, of which if you look at the superscript node here, all right, if you look at the superscript node, you should be able to see these. What does it stand for? At standard state, that means the pressure should be 1 atmosphere, concentration 1 molar, and temperature 298. That's what it stands for. So when you look at these values on table 1, we're going to come back to this. It is at standard state. And it is the ease at which each of these ions can be easily reduced. That means adding electrons. If it is positive 2, we are adding 2, 3, and so forth. And it is measured against what we call shear, or standard hydrogen potential. As you may have seen this in your chem book, shear means standard hydrogen electrode. So these values were determined as a function of this shear, standard hydrogen electrode, standard hydrogen electrode. So if you think of electron being transferred, let's see this illustration right here. If an electron is moving from, say, sodium, all right, to chlorine on this side, become negative, positive here. If an electron is being transferred, let's see, this is redox reaction. An electron is being transferred from sodium to chlorine. In this case, sodium is a reducing agent. Chlorine is the oxidizing agent. It's making the other guy to lose, and so forth. That's how you look at that. Now, keep in mind the flow of electron. All right, the flow of electron. Remember, when you charge your cell phone, right? When you run out of juice, that's what I hear most people say out there in the street. Like, I'm running out of juice in my cell phone or my iPad. What is happening in the cell or in the battery is like this. Look at my fingers. That electrons are somewhere here, and it got to flow down so that electricity is generated. It's just has to do with electrons moving from point A to point P. And electrons are what? Electrons are negatively charged. I'll come back to this table again. I want you to understand what this standard state means. We will be using that. Now, in generation of electricity, all right, in generation of electricity, there are two types of cells. There is the voltaic cell, all right, and there is the voltaic or galvanic cell. There is the electrolytic or galvanic cell. I meant to use this. There is galvanic or electrolytic cell. So if I talk about galvanic, voltaic, this is voltaic right here, voltaic cell like that. And there is electrolytic or electrochemical. Some use electrochemical. In our case tonight, the type of cells for this type of reaction is the the voltaic cell. This voltaic cell or carbonic cell uses spontaneous chemical reaction to generate electricity. Right somewhere, because they might ask you in your final exam, differentiate between electrolytic or galvanic cell, or if it is a structure that explain, you should be able to state that. This galvanic cell or voltaic cell, which we are going to use today, use spontaneous chemical reaction to generate electricity. Or in other words, electrons will spontaneously flow from point A to point B, all right, spontaneously without any external influence. Now, in electrolytic or electrochemical, there should be a continuous, all right? There's a continuous source of energy to drive the electron from point A to point B. Electrons will not just move from A to B in electrolytic. I'm going to draw an electrolytic cell, which I know some of you already know. Let me just, I should have align this so that you look at how it look like. Let me align this so that I'm gonna get rid of this. And I'll draw the galvanic cell, this one. Let's forget about this. What I'll draw is this electrolytic, no, voltaic cell. Oh wait, there is what we call, all right, there is what we call the anode, all right, and there is what we call the cathode. You should be able to, cathode, it's hard. I wish I could use my iPad, but not today. And then there is what we call here, this is soul bridge. I know some of you know what soul bridge is. All right, soul bridge. I should have just go all the way to the solution right there. It should go in the solution, and we have here solution. We have their solution, and they have different solution. In this case, let's use anode and cathode. what is, let me ask you this, because I know you have looked at this, or I know you can draw this, I know you can label this. What is the sign on anode? What is the sign? Is it positive, negative? Which side is negative? Which side is positive? All right, let me back up. Are you familiar with what I'm trying to draw here? Have you ever seen this before? Do you know where I'm going with this diagram? Are we all on the same page? Amy saying yes. Amy, what is the sign on anode and what is the sign on cathode? It will help us also in the calculation. Don't say, why am I going through this? It will unlock how we will proceed with calculation in B and in part A. Unless we understand this diagram, anode is negative and cathode is positive. Yes, thank you. That's correct. So if I label this as negative and this one as positive, all right, here, what takes place here is oxidation. Loss of what? Oxidation. And here there is what? There is a reduction. That means we are adding electron, we are losing electron. And oxidation is loss of electrons. So if that is the case, we will expect there is, I forgot to put what we call electrodes right here. There is what we call electrodes on either side. Maybe I should have used a different, color for that so that you look at it. So if I have here and I have electrode, this is electrode immersed in some solution. Now there is a wire. There is a wire now for electrons going from here. And if electrons are flowing, you will see the bulb right here, lighting like that. Solution right here. The electrons will flow from this side. This is the flow of electrons. Flow of electrons. This is the flow of electrons from cathode to from anode to cathode. From anode to cathode. Mostly, you'll see in most texts they use this as zinc, and they use this as copper. Copper. We are adding electron. We have copper ions right here in the solution, and then we have zinc right here. I don't want to go in details on, solar bridge. It just provide an electrolyte to balance the ion, and with time, this will become thick. Like, there will be some ion being deposited because of this reaction. Cu. What is happening here is, if it is positive 2, the ions in the solution will be reduced with the two what? With the 2 electrons to become solid copper. It's important to know the physical state. This is aqueous right there. All right, and on this side, we have zinc. This one will go away. It will, with time, it will just reduce. It will be eaten away. Since we are losing zinc metal, that means oxidation. This is solid to go to zinc like that. Zinc to positive and plus 2 or plus 2. 2 electrons. These are 2 electrons like that. So we are losing electron. On this side, we are gaining. This one is more clear when you look at the electrons, where it's coming from, where it's going. The number of electrons being lost equals the number of electron gain, from balancing redox equation. If I was to write just a general equation. You'll see this written as n, all right, n, all right, n going to plus Cu, and then you'll see solid. I don't want to go in details into the double line wanted to represent, but let me just simplify this and make it Cu, this is solid. It represent behind the scene the two reaction. This is solid plus now zinc ions. This is aqueous. It means two ions. We have lost two. You have to use the coefficient from here. This is a redox reaction that they represent this. They represent this. Now, there is what we call cell potential. Cell potential is, all right, let's see if I can save this. Cell potential. If I have cell potential, let's see this. I'm gonna erase this and show you how we can determine the cell potential. This can allow me to get a new page. That's why my iPad, I could just click and go to the next page and go to the next page. Now, cell potential is determined from this equation. Standard, remember, standard cell potential is obtained from E cell. The electromotive force for the cell is obtained from this equation. E cell equals to E for the cathode standard, right? Minus E of the anode. Which page in the lab manual is this equation? Can you see which page is this equation? Which page is this equation real quick? We gotta move fast. Page 181, yes, page 181, you have this equation. Thank you, Glenn. On page 181, this is the equation used to find the standard cell potential. We will be calculating this term, or we will use this, and you should be able to identify which one is the cathode, which one is the anode, which one is the cathode, which one is the anode. I'll go back again to the table. Table 1 to help you see how to identify the cathode and the anode. Let me, I need to erase this because they don't go away. And it will be over my table. So I will minimize this and go to this table right here. Remember, cathode minus anode. Cathode minus anode. If I look at this diagram right here, given any two, you should be able to tell which one will be my cathode, which one will be my anode. So that you plug in that equation I just erased, which is on page 181. This is how I've, I've figured it out, and it is much easier. I don't know if it's gonna be easier for you, but just for the sake of the lab, this is how you use this table to identify the cathode and the anode. And it's very simple. Watch this. Remember what I say, electrons got to flow from higher to low. Otherwise, when it is of the same potential is when you run out of juice in your battery. Like if it's the same, there should be some potential for electron to flow from high potential to low potential, and in the process, electricity is generated. Otherwise, if there is no flow of electrons, just the same level, no electricity will be generated. And electrons are what? They are negatively charged. So if given two reduction potential here, the one at the top right here, the more negative is your anode, which is more electrons. Look at that. Electrons are negatively charged. So that one, the more negative will be my anode. The less negative will be my cathode. Remember positive and negative, that's why I had to label that diagram. Hope you are drawing that so that you see. Look at these first two right here. Somebody will say both of them, they are negative. I can tell that this can be my anode and this can be my cathode, because this one is less. I can say more positive. This one is more negative, and electrons will flow from high to what? To low, to positive. With that, you can now say cathode minus anode, cathode minus anode. That's how you look at all this. Even if I have both of them here, like all of them, they are positive, I'll say which one is less positive, even though this will be my, this one will be my anode. Compared to this one will be my cathode. That's how you look at it. Even though you may be given both of them positive, that's how you can identify cathode and anode. I can pick something the author uses. For example, this is on page 181, yes, Clenis right here. This is the equation. How will I know which one is cathode, which one is anode? The more negative will be the anode, the less negative will be what? Will be the cathode, so that when you plug on this equation, you'll get the standard cell potential. If you look at what the author uses, for example, lead and zinc. So if we have right here, forget even about, what goes on below here. We're gonna come back to this equation. But if I look at this, how will I know which one is my cathode, which one is my anode, to calculate the standard cell potential, not the cell potential, standard cell potential. Now, I will go to this table and look at zinc and what? And lead. If I look at zinc, if you look at zinc is at the top right here and lead is at the bottom right. So this will be our anode. And below it, which is positive, will be our cathode. So we'll say negative 0.1263 minus minus. Remember, it is minus minus to change it to positive. And that's why you see here the author is using this equation so that you know, how do I know? When you just look at it, suppose something else other than what is given in the program, how will you know? That's going to work for all cell potential. If you are calculate, or if you are asked to calculate the cell potential for something like that, no equation. That's how you look at it and say which one is my cathode, which one is my anode. So this is cathode, it was more positive. This one negative were the electrons. So cathode minus anode. And remember, this is minus minus to change it to positive, and that's how you find the standard cell potential using this equation and this table right here. Let me take a pause. Is there any question on using table 1? Is it table 1? It's not even labeled as table 1. Let's just say standard reduction potential table. And this is standard. That means 1 molar is the concentration of our solution, if it is aqueous. And right here, that means the concentration of all this is 1 mole. And the atmospheric pressure is 760 millimeter mercury, or 1 atmosphere. And the temperature has to be in maybe 298 or 25, doesn't really matter, but standard state. Is there any question on how to calculate the standard state using the standard electrode potential, reduction potential? That is how you use that table. You will be doing the same thing. The key thing is identifying the cathode and the anode, and you plug in the equation. Please be careful on negative and negative. Some students forget about, the negative, and then they just say this minus that, and then they end up with the wrong value, So if I look at these two right here, I'll just go and look at the reduction potential for zinc and copper. So if it is zinc and copper, zinc is right here and copper is down here. So this will be my cathode and this one will be my anode. Remember, anode was negative and cathode is positive. So that's how you use this equation with this table, using this equation on page 181 with this table to calculate the standard cell potential, the standard cell potential. Now, enough of that. So, suppose we are not working at standard state. For example, if we were to come to the lab and do the experiment, there is no way we can adjust the parameters in the lab in such a way that the temperature is 298.15, pressure to be 1 atmosphere, and work with the concentration of 1 molar. No, even in the background, if you read, we will not be working with 1 molar. If you look at the direction here, we will be working with different concentration of copper. It is not 1 molar, so it's at non-standard state. That's what I'm trying to say. The lab experiment is not in a standard state, yet we are expected to calculate the cell potential. How are we going to do that? Cell potential. If you look at the data sheet, let me see if I have my data sheet. I think it's right here. If you look at the data sheet, you'll have to calculate the cell potential. It's not non-standard state. I don't want you to make a mistake of, using the equation at standard state. No, we use what we call Nernst equation. This term right here at the top, the title of the lab right here, all right? Nernst equation right here at the top, this is an equation, all right? This is an equation for calculating cell potential. That is, you have an anode and you have the cathode at non-standard state. All right. This Nernst equation is used to calculate cell potential at non-standard state. And that is the equation you will use in determining this column on your data sheet. Determining this on your data sheet. So I'll be juggling between data sheet and the background procedure. So what is all this about standard Nernst equation? I've walked you through how to calculate at standard state. You have to refer to the table. Yes, there is no way out there. In the standard state, you have to use table 1 and that equation on page 181 to calculate the standard cell potential. And then cell potential you see here is non-standard state, and we use what we call Nernst equation. A Nernst equation is of this form. I don't want to, you can read, go back. This is the Nernst equation right here. This is the Nernst equation right here. Which, this part right here. I walk you through that. This is from anode minus cathode. I mean cathode minus anode. This is from cathode minus anode. When you look at this, it's standard state. This is non-standard state, which you need to complete in the data sheet. When this, I don't want to go in details here how we end up with. This is a constant which comes from the room temperature. We assume that we are working at 298. This is the R constant and Faraday's constant. Manipulating in this equation, you end up with this value in volts, and N stand for number of what? Number of electrons transferred, number of electron transferred. So it depends on the combination. It depends on the construction of the galvanic cell. Some cells transfer 3 electrons. Some cells transfer 1 electron. Some transfer 2 electrons. So N stands for the number of electrons. In case of lead and zinc, 2 electrons. In case of copper and zinc, there are 2 electrons. And you're going to substitute this N with the number of electrons, with the number of electrons being transferred. What is this concentration of product over reagent? When you write the equation, remember when I was illustrating the galvanic cell and saying this is the solvent, this is the anode, this is the cathode, you know, and then I write the equation without showing which one is the anode, you should be able to see which part is the reagent, which part is the product. For example, right here, if you look at this equation, I'm going to circle, all right, I'm going to circle only the what is relevant to us. This is the reagent. This is the what? Product. So that when you look at the concentration of the product over concentration of the reagent, it is based on the equation. Based on the equation, how it is written, which one is losing, which one is gaining. All right, which one is losing, which one is gaining, and you rewrite the equation so that you know the concentration of each one of them. That way, you will be able to plug it in this equation: product over reagent, concentration of the reagent, number of electrons. If I go to data sheet now, you should be able to read the background procedure. Otherwise, it's not just you go to the data sheet and you need to read the background. What I mean by background? Here on the data sheet, let me walk you through how you're going to do the full series right here. Concentration of copper 2 ions in the experimental cell. This is cell 1, this is cell 2, this is cell 3, this is cell 4. Each cell has different concentration of copper 2. How will I know it? It's assumed that you came to lab and then you read the direction and then it tells you the concentration. For example, in cell number 1, from the procedure, right here, you have to read each and every statement, each and every sentence, all right? Right here, get another dry clean beaker and using graduated cylinder provided in the hood for copper 2 solution, get 50 ml of, take note of the measurement as well, 0.025 molar copper 2 solvent. So this is the concentration of for cell 1. For cell 1. Now, if you read all the way to the last step 9, repeat the above so that the final concentration of ion is 1 molar. So we are starting with 0.25, 0.5, 0.75, and then 1. That is what it means by until. So we are starting with the concentration of 0.25, all right, 0.5, 0.75, and then 1.0. You have yourself what? The concentration of. And remember, in each cell, what is the concentration of your what? Concentration of zinc. because you're gonna have zinc and you're gonna have what? You're gonna have copper as well. Which one is your anode? Which one is your cathode? I've walked you how you're gonna figure it out. This you can read this. You're gonna feel that, so that you use the Nernst equation now to find the calculated. Right here is the calculated. I'll say here, let me just label this. This one right here, this column right here is, let me say, calculated, using the Nernst equation. This one, point what? 0.25, and all the way up. And then this one we use the Nernst equation. Write the redox equation such that you have the reagent, you have the product, so for this column to work. So I expect to see 4 Nernst equation for this side, for this one, for cell number 3, and for cell number 4. And of course, percent error, right? Percent error is the Nernst equation, absolute value between the two over Nernst equation. You get the percent error. Any question on part 1, please? Any question on part 1 before I move on to part 2? Any question on part 1, please? Any question on part 1 before we move on? Amy is saying, nope, you understand, we are all on the same page. Please read again the background so that you know the concentration. I wanted to show you the percent error is on page 190. Look at page 190. For this column right here, page 190 on how to find the percent error. Once you have this value and this value, you use the equation on page 190 to find the percent error for percent error. So the key thing is understanding this, how to navigate the Nernst equation. When they say E cell here and then they say Nernst, what does that mean? It means use Nernst equation. I showed you what it means. I've explained what it stands for, where to find the values, plug in there, and just move on. It's gonna be different for cell 1, cell 2, and cell 3. Let's move on. I'm just gonna move on to part P, all right? Part P, having gone through that, part P is the calculation of using, still Nernst equation to calculate or generate values to calculate the formation constant of this complex. Formation constant of this complex. And the formation constant, it's just like Kc. Remember Kc? From the all the way equilibrium, it is product of what? Over reagent, concentration of the product over reagent raised to the coefficient in the balanced equation. Raised to the coefficient in the balanced equation. All right, just Kc or Ksp. Remember Ksp expression? I want you to have in mind that this is from concentration of what? Concentration of the product raised to coefficient in the balanced equation over concentration of the reagent R over coefficient in the balanced equation. So with this in mind, in order to get this value here, this is what's going to happen. Remember I stable, but this one is slightly different. This one is slightly different, but it just looks like an I stable. This is like an I stable. We need this value. If we can get A, if we can get B, and see here, we can get ourselves Kf, formation constant. And remember, all right, APC, APC here, or product, this is the equation. This is the equation on the calculation part. Look at this equation right here. Everything is aqueous, which means Kf, that is the formation constant of the complex, copper 2 tetramine complex, is concentration of the complex Cu NH3 4 2 positive. What is the coefficient? It is 1 over concentration of copper 2 positive. The coefficient is 1 times concentration of NH3 raised to 4. NH3 raised to 4. If we can get the values for all these species at equilibrium, and then we can plug in N to determine the formation constant of a complex. It's not going to be easy. It's just the way you do the ice table. First of all, you got to understand we are working with moles, initial moles, because all these reagents have different, they have different, or we have in different moles, volume, the volume of this and the volume of that. Look at the volumes. 50 and 20, that's the total of 70 ml. So that when you calculate the concentration right here, the equilibrium concentration for NH3, which is this one, the concentration of this guy right here at equilibrium, it is a function of the total number of moles. So before you fill in this last in terms of molarity, which you have to calculate separate, it's not the one you just subtract from ice table and you'll have to calculate how many moles at equilibrium, how many moles at equilibrium, and then it's a function of the total, volume. So I need to know the number of moles. I need to know the number of moles. The way this has been designed, this one is in excess. This one is in excess. In case you are wondering why this guy right here is black, well, it's not an accident or it's just by default. It means whatever you have here, if it is, let me just pick it 2 and 5 here. Initially, we don't have the complex. Remember how it goes before you mix the two? We don't have any complex. That's why we have it here as 0, 0. Now, this is the limiting reagent. That means all the number of moles will be consumed. Theoretically, even though it's not the case, but nothing will remain. So use the stoichiometry here and say, all right, mole ratio is 1 to 4. 1 to 4. If I have excess of ammonia, how many moles will be consumed and how many will remain? X, remain. You have to do how many moles remain here. When the reaction, this is the limiting reagent. So nothing will be, essentially it will be consumed. That's why it's flat. If it is 2, that means we'll have 2 moles. I'm just using this as an illustration. I didn't put here because you have to do the stoichiometry here to figure it out that how many will be used to, remain. And then at equilibrium, number of moles at equilibrium, you will use the number of moles at equilibrium to calculate the molarity. So you start with moles. I want you to look at what's happening. The first two here is working with moles. You're working with moles here. So that if I have a number, if I have 2 moles, you don't bring 2 moles right here. It will be 2 moles. Let me just put here 2 moles, you know, because the 2 moles here will end up eventually being the 2 moles of our product. It's just, you know, once mole ratio is 1 to 1. You see, mole ratio is 1 to 1. That's why I'm using 2 and 2 over 70. Not 70, but 0.0 liters. Why am I changing these to liters? You know, molarity. All right. You're going to find the number of moles here. If you know the volume in ml and the concentration, the molarity and the concentration, you can find the number of moles. Initial number of moles, molarity times volume in liters. Concentration of the complex is the number of moles over volume in, this is total volume. That's why I have 7. This will give me the top part right there. Are we together? So far, so good? Can I get a yes on the chat feature, please? Are we together on how to find the number of moles? Clan, Danielle Edwards, thank you. I've shown you how to find the molarity of the complex. The first two is you're working with moles, but when you get here, you switch the gears and find the molarity. Look at the molarity here. Now here, when you subtract the starting number of moles from here, from the stoichiometry, you will find the molarity of this. So you shouldn't have any problem with the last two here. These are our, this is the product right here. Right here is the product. And this is the reagent. And then the question mark here, you can find this because something will be left over. You can do the mass and find the concentration. You know excess reagent, how many moles will be left over, divided by the total mole or total volume, you get the concentration. This question mark I have here, even though we assume that everything will just be converted to the product because it is a limiting reagent, there is still something in the solution which will conduct electricity. Some trace amount of copper ion you see here on the, it will be left over. There was something, and that is why, all right, that is why I have here, look at this, that is why the measure, let me erase here so that you see this, what I'm talking about. On this one, this measured potential, look at the measured potential here. For the last part right here, measured potential after introduction of 20 ml of zero solution. That is when you mix, this was the potential. That means there was still some ion, copper 2 ion in the solution. This is the measure. And we will use a Nernst equation to find. You will use Nernst equation to find this question mark from the Nernst equation. How are you going to use that? Let me back up to Nernst equation. All right. Let me back up to Nernst equation and show you how we're going to use the Nernst equation. Yes, this is the Nernst equation. This is the Nernst equation. Log of, all right, or product over reagent. I'm gonna use this so that, all right, you know this, and I want you to follow the example in the text. You know this, this is the measured, this is the measured, The one given on the data sheet. Look at your data sheet, everybody, you have that. That is the measure. You can use the standard cell potential here from the table. Look at the table. Number of electrons, and then concentration of the product over concentration of the reagent, concentration of the reagent. So if I know the product and reagent here, you know the product and reagent on the data sheet. Let's see, where is it? Right here. These are, all right, these are, look at this. You know this part, you know that part. How about from the equation, from the calculation? Where is my calculation here? Copper 2. So 2 electrons. You'll get the 2 electrons, use the Nernst equation to find. The measured here is the 0 point. This is the measured value. This is the measured value here. Measured potential, that is the E of the cell. If I can, look, if you can find out the concentration of copper 2 tetraamine ammonia, that means you know this and you know that, you have only one species which is missing in the previous reaction in your reagent. You will manipulate the equation similar to what we have in the, there is an equation here for rearranging. If you look at all the way to 185, all the way to 185, starting from, all right, starting from a solution which you are given. This is the setup, how it look like, how it look like. This is the cell potential at non-standard state. This is what was measured. You'll calculate the measured potential, all right. You'll calculate the measured potential for ammonia, think that, and plug in the equation for Nernst equation to get the concentration. Similar to this, if you look at the calculation here for, no, this was given to calculate. There is one right here where we were looking for concentration of lead. We don't know. We have to use Nernst equation, see how many electrons were transferred. You rearrange the equation in such a way that you will have the concentration of lead. Similar for copper, you'll proceed in a similar fashion all the way until you get the concentration. It will need a little bit of, algebra, page 185, on how to arrive at the concentration of your copper. So this, in a similar fashion, you will have to calculate the concentration of copper 2 ion in the solution so that you have the values to plug it in the equation on how to find the formation constant of copper 2 tetraamine complex, the formation constant. Here you can just use the common knowledge. What is new to you is probably how to use the Nernst equation to find the concentration of uh, copper 2 ion left in the solution. Although we say it's a limiting reagent, something still will be in the solution, which you'll use Nernst equation to find out, plug it in. And you are given the literature. I think you are given the literature value for the formation constant right here. Compare your value with the literature value formation at 25, in the neighborhood of that. Hopefully you'll be in the same region. Please read this section here on how to find the concentration of copper. What is challenging will be right here. You see this right here. Otherwise, you use the equilibrium moles here. Use equilibrium moles here to calculate the concentration of ammonia and the complex, but use Nernst equation and the new black foil, and that will be it. Any question? Any question? If there is no question, you can just get started. If you have any questions, send me an email and I will get back with you. If you need one-on-one, I will plan to or schedule a live Zoom conference one-on-one with you and walk you through on how to complete the calculation. Please show your calculation in your workout and turn in your work through Canvas. Put it in the respective folder. Please do not send me as an email attachment. It will be hard for me to create and too much work printing out. I don't have even ink printer and I don't want to go out there. Otherwise, the class is dismissed if there is no question. It was nice being your instructor this semester. Be safe and stay safe. Practice social distancing. Thank you. Class is dismissed.